Now we'll go on to false discovery, which is falsely saying something exists when it does not. And this is what the p-value contributes to reporting to, and this is still part of frequentist inference. And I'll use the example of screening tests, where a false positive in diagnostic tests is similar to false positives in significance testing. And the common example I give of a false positive, as in what is a false positive, is the boy who cried wolf. Because the first time he falsely said that there was a wolf, there was not. He thought it was funny. The second time he did the same. The villagers came, there was no wolf. The third time was not a false positive, that was a true positive, so there actually was a wolf, but no one believed him, and then all the sheep died. So we also need to talk about the power when we talk about false discovery. So power is the complement of beta, or the conditional probability of rejecting the null hypothesis given that it is false. But going back to screening tests, the power of a significance test is the same as the sensitivity of a screening test. So when a real effect exists, what is the probability of detecting it? And I think this paper from a few years ago is a very good example on false discovery, where they use an example in, say, 10% of tests, there is a real effect, so the prevalence is 10%, and the power is 80% or 0.8, and the p-value is 0.05. So when we think about it in this flowchart, in the natural frequencies, we find that this is much easier to understand as we were shown on Thursday. Considering 1,000 tests, 100 of those 1,000 tests have a real effect where the null hypothesis is false. So that means the power of 80% is such that 80 of those 100 tests, the real difference is correctly identified. And then the remaining 20 are those falsely identified as having no difference when a real difference exists. So that's beta. For the remaining 900, where the null hypothesis of no effect is true, the p-value of 0.05 means that 855 correctly identified as having no effect, and 45 falsely claim a difference exists when it does not. So to calculate the false discovery rate, it is the number of false positive results divided by all positive results. And 36% is actually a lot higher than the 5% that people would be led to believe. The p-value accounts for an unknown prior distribution, and the details of that unknown distribution can make a difference in the false discovery rate. And I'll go through this paper, which shows this very basic and understandable formula for calculating the lower bound interval for the likelihood ratio and for alpha, the type 1 error, of rejecting the null when it is false. But more importantly, from this paper, they can figure out that the false discovery rate at a p-value of 0.05 is at a minimum 29%. So you're going to get it wrong 29% of the time as a minimum. And if you pick the value of, or the threshold of the p-value to be less than 0.05, which actually means in most cases it's between 0.01 and 0.05, because if it was less than 0.01, they call it less than 0.01, then the false discovery rate could be between 11 and 29%. Going back to the problem of false discovery rates in frequentist inference, this shows that they are clearly underestimated, meaning that there are more errors of falsely discovering an effect when it does not exist, meaning that the error rate is higher than actually reported.
A roulette wheel comes up. I could have listed any 4 numbers here. The p-value for that is 6 times 10 to the minus 7th. Very rare. Very rare. Does it mean anything? No, because you have to get 4 numbers. However, now it's evidence if you notice that the numbers are adjacent. Maybe there's a dead part of the wheel. Maybe it's weighted. Maybe it's tilted. What makes it evidence is that there's another explanation that predicts what you saw better than chance. That's what creates evidence. We can't talk about evidence unless you're literally talking about 2 competing explanations. And this is where Fisher's method sort of fell down. It said the null hypothesis isn't true, but it didn't have an explicit measure of, well, if it's evidence against that, what is it evidence for? And if you remember, and I'll show you again, that's what the Bayes factor was. It was it was how probable is this observation under one explanation versus how probable under another. And we will see that that is in many ways at the heart, one of the things at the heart of the difference between, unbelievably, between Bayesian and standard frequentist. That is, you always consider what something is evidence only when you consider it in the context of two competing explanations. So you have to explicitly put in there, it's not just implicit. You can't just say, I'm thinking about whether the treatment works. You literally have to say, you know, what is it? Is it evidence for a 5% difference? Is it evidence for a 10% difference? How strong is that difference? A p-value of 10 to the minus 2 tells you nothing about the treatment difference that was seen. If it's a very, very large study, it could be a tiny risk that would have that p-value. If it's a very small study, it would have to be a huge risk. So there's no information, which is why the results of very small studies are often implausible, because they involve huge risks, which we come to the table thinking are not really very likely. This is the last thing I'm going to show you, which is sort of a Rosetta Stone for translating p-values into, there isn't a unique Bayes factor, but there is sort of in a sense, the strongest Bayes. You can do a mathematical translation to the smallest possible Bayes factor, and that is the strongest evidence you can claim against the null hypothesis. And what you see is that these numbers are much higher than these numbers. That is, for a 0.05, p of 0.05, the smallest Bayes factor you can get is about 0.15. That is about 1 in 6 or 1 in 7. That's the strongest evidence you can claim. And if you plug that into Bayes' theorem, that gets you from a prior probability on the null, so I've reversed this, going from 75, driving it down to 31%. If you start at even odds, it drives it down, the null hypothesis, to 13%. That means even if you observe a p-value of 0.05, if you started out with a even odds, there's still a 13% chance that the treatment doesn't work. If the null hypothesis is highly likely to be true, p of 0.05 doesn't drive it down very far. You're still a 1/3 chance that the null hypothesis is true, that the treatment doesn't work. So I guess the bottom line is, in terms of words, that p of 0.05 in the 0.01 to 0.05 range is actually very modest evidence. It's pretty weak. And that unless you come in with a very strong belief that a treatment works, it's not going to raise the posterior probability up to the 95%. That's what Bayesian analyses will show. Features of his methodology. The p-value was calculated deductively, but it was intended as an inductive measure of evidence in a single experiment. It involved only the null hypothesis. You will see how critical this is. It was meant to be informally combined with other sources of information. And you will note here that I haven't mentioned anything about rejection or acceptance or anything like that. It was a guideline for inference, not behavior. That is, it was part of a tool in the scientist's toolbox. And this is what he said about the 0.05 level. If 1 in 20 does not seem high enough odds, that is to decide that a phenomenon might be real, we may, if we prefer it, draw the line at 1 in 50, the 2% point, or 1 in 100. Personally, this writer prefers to set a low standard of significance at the 5% point and ignore entirely all results which fail to reach this level. He says, a scientific fact should be regarded as experimentally established only if a properly designed experiment rarely fails to give this level of significance. Now, do you understand what the implications of that statement is? So this is what's significant. This is where the word significance came from. So he developed that. Significance is simply that if you do an experiment and it doesn't rise, it doesn't even cross this low bar. That's what he set the bar low, so he could safely disregard everything that was non-significant. Initially he didn't design clinical trials. He designed agricultural trials. That's what he did, which could be repeated over and over. So he set the bar of evidence very low for significance, so he could, quote, safely ignore everything that didn't reach that point. And then he said, if you do the experiment over and over and over again, and every time it's significant, then maybe it's true. He, in no way did he ever think that this would be used to establish truth in one experiment.